Hello, and welcome to my presentation for the Informs annual meeting of 2021. My topic today is on the online control optimization of material handling systems and what I think is a pretty novel application for OR in the industrial setting. So without further ado, again, I'm Richard Schrade. I'm the co-founder of Automation Intelligence. We're an Atlanta-based company, a small company, almost 3 years old, and based right near Georgia Tech's campus in Tech Square. And we focus on making industrial automated systems smarter, more efficient, and more accessible. So just briefly, here's a list of clients that we've worked with so far. Not very important. And getting right into it. So today's agenda, we're going to talk about the application for OR, and in this case is a material handling system, of course. We're going to get a little under the hood and get a bit scientific with some of the optimization constraints and formulation of the model. And then we're going to talk about some of the softer things, less technical things, the impact that we had on improving the system and how we went about integrating this OR application with the industrial controllers. So if there's three things that I'd like to get across in my talk, the first and foremost is that there's so many opportunities for OR applications in industrial automation. Automation consists of, especially in the industrial setting, robots and conveyors and a lot of things that just do what you tell them to do. They're very deterministic in a lot of cases, and that makes, with less variance, it makes optimizing a lot easier. But at the same time, there's a perception of risk of changing the way things have always been done, right? And sometimes competing interests that may hinder innovation in some cases. But the point is that you can improve the performance of your industrial automated system in a lot of cases with only swapping out the logic, with only changing the algorithms. And you can quickly, almost overnight, get a boost in your ROI, without any new equipment or new procedures or things like this. So today's application is going to be about a tilt tray system that carries, you can think of them as packages, or these are widely used in airports across the world. But the idea is that in this case, packages are inducted onto a sort of a carousel of trays, and they will ride the carousel to their destination, and these trays will tip over and discharge the package or the bag or whatever's riding on them onto their destination. So we'll just watch this for another minute or so. All right, so let's jump into the problem itself. So in the video you just saw, you had trays that were identically spaced and they had identical size. And in the application we're going to discuss here is actually where you've got two different pitches of trays, or two different tray sizes that go in a pattern. And in this case, we're looking at two 600 millimeter trays back to back, followed by two 1 meter trays back to back. But the application is essentially the same, right? You've got various sized boxes on induction belts, which we've got here is induction belt A and induction belt B. And then you've got this tray carousel that's moving, and in this case, to the left at some speed. In this case, we're considering 250 feet per minute. So the analytics problem that we're trying to solve is which parcels, which packages, or which bags should we put on each tray such that we can maximize the throughput density of the carousel itself. So that's the analytics problem. Now you can imagine that when you've got boxes of different sizes, then in some cases you may need 2 trays, and in some cases even 3 trays. So there's many different options, especially when it comes to large packages, on how you can choose to place them on the trays. And so we've got 3 different sort of categories here: a blue box, which is the smallest; a maroon or a red package, which is a medium size. So it wouldn't fit on just a small one, but it would fit on 2 back-to-back 600 millimeter trays. And then we've got the largest one, which would be a 3 tray scenario. Either 2 of the large trays or 3 of the 2 small and 1 large. So you can imagine the various options, even with just 7 packages here that we have on this carousel. So how is this done already? What did we start with? We started with a heuristic. So when I say we started with, this is what's sort of always been done, right? This is for many, many years been the logic that's been employed for assigning packages to these trays. It's a heuristic. It's essentially a very static algorithm, and the algorithm is assign the package to the first compatible location in order of arrival. So this is a first in, first out, or a FIFO system. And if we use this heuristic again on this representative example we've got on the screen, this is going to be the solution that we get. The first package from each lane is inducted in sequence, followed by the second one, finally the third one. And if you were to take a measurement on the density of occupation of these trays, essentially how many of these trays are occupied, you would get 100%. And so we're going to talk about a little bit why that might be a misleading metric, and why package density, the number of packages on the carousel at a time, would be a more useful one. So now we're going to look at what it would look like if it were to be optimized. And in this case, we're not looking at a static heuristic. In this case, actually, we're looking at a mixed integer program and an assignment model that's within the constraints of the system and within the constraints of sequences and things like this. It's assigning packages to the trays based on that which is available to it. So it's got all of the options available, and what does this look like? So we're going to go back to the heuristic in just a second, but just to point out, we do start off similarly, where we take the first package from each of the induction lanes, but you see something different here. This A3 package has been moved up. And so it violated that FIFO rule, that first in, first out rule, because the third package from the induction lane A is inducted before the second package from B. So why is this better? So let's go back now and look at the heuristic. So this is, again, the previous version. Well, the B2 package was such that it was greater than 1200 millimeters, right? This would have required 2 of the 600 trays and then 1 of the 1,000 as an overflow. And so since that's what's required, that's what was assigned. And you could see the A3 then took the next tray after that. So now let's go back again to the optimized version and see how that's different. Now we've got a small tray for this A3 package, a small package, perfect. And the B2 is now taking up 2 trays as opposed to 3. 2 of one of the small and 1 of the large trays here instead of 3, and then A4, as you can see on the right there. So again, what we're doing is we're improving upon a deterministic heuristic that's been used for a long, long time, and applying a mixed integer program to maximize the package density on this carousel system. And I intend to be watching this during the presentation. So I imagine at some time in the future, there's going to be a chat box. As you have questions, please feel free to type them in whatever chat box exists, and I'll be happy to, during the presentation, answer your questions. So moving on past the problem, Now we're going to talk about how do we integrate it. I think that this is almost even more difficult than formulating the OR problem, is getting it to the right place to solve the problem in the industrial environment. So this is a sort of a representation of what the communication stack looks like at a distribution center or even a manufacturing facility. Essentially, at the very bottom, you've got your plant floor, right? You've got your conveyors, you've got machines, you've got robots, and these objects, these automated systems, are consuming information and producing information. So, you've got robots which are being told where to go, what to do, when to pick things up, where to place them. But at the same time, you've got sensors. You can imagine sensors as scales or proximity sensors, or even just ones and zeros for photo eyes. This is photo eyes blocked. This photo eyes cleared. Even scanners and things like this. So this is the plant floor essentially, and then there's a few different protocols for how the plant floor gets its information. And we're not going to dive too deep into this, but essentially, there's the level 1 and 2, which is the lowest level of communication and of intelligence, and that's where you've got what's called PLCs, or programmable logic controllers, which communicate with other programmable logic controllers, as well as other information systems on that layer. And that's actually where we are integrating this process optimization tool, is with the PLC, with almost at the lowest point of attack for this communication stack. You can imagine if you getting to level 3 and level 4, this is typically where optimization is applied, right? Warehouse control systems and manufacturing execution systems a lot of times have scheduling agents that help maximize utilization of equipment, and that's a very common application for optimization. And so this one's a little bit lower, and something that we need to interact with a little bit more frequently. So let's take a bit of a peek under the hood. I want to, without getting too deep into things, kind of just show what our formulation looks like. This is obviously not the final representation, because that would be in computer code that's, again, communicating with the PLC, but just a formulation that we use to document it. And this is, I think, a really interesting constraint. And this is where we capture whether or not we need 2 trays. If we were to use those 2 trays, that we assign only 1 package to each tray. So let's take a deeper look here into this constraint. So this essentially, what it's saying in English, which I think is helpful, is that if package P is assigned to tray T, and that's that X term right here, and the package is longer than the tray, so that's what this expression is here. And let me see if I can get a laser pointer going. So if the package is longer than the tray, this is greater than 0, then P must also be assigned to the next tray in sequence, which is this Y term, right? So this is YP, package P, and T plus 1, which is that next tray. We do have a constraint for 3 trays. So this captures only those which are 2 or more trays. And then we do this for all packages that exceed the length of the tray. So packages that, for all of the packages, for all the trays that for which that package is longer, and then for all the trays. And then we've got an M term that we use to force this assignment Y in the cases where this is true, where the package is indeed longer than the tray. So I think this is a really interesting constraint. There's obviously other constraints, like sequence constraints, right? We can't, packages can't jump each other in line. There's various other ones. Another interesting one that we could have shown is that every package must have a tray. And we'll talk about sort of how much we know about these trays and when we know them in just a moment. But this is, these are some of the other constraints that go into this model. So let's dive a little bit deeper into the integration. So we talked about what a PLC was and where that lives, and it's actually typically very close to the equipment in a electrical cabinet or something like that. And then for those who may not be familiar, this is what a PLC looks like. And in this case, we've got a few different other PLCs and computers in our rack, but this is what it looks like. And so our application, actually where our mixed integer program and solver live, is in the cloud. And so so this presents a few interesting challenges to us. But essentially what happens is that every so often we get a message. We send the package and tray info. These are the packages we have. These are how long the packages are, and same thing for trays. Here are the trays that we have available to us, and their sizes, and we send it to the cloud. So it has to go through a local network switch. The plant network speaks to the outside world and reaches out through an API call to our application. This is where we read in that package and tray information. We build the mixed integer program, and then we send it to a compute server to solve. And we need this to happen very quickly. Obviously, once we get it, we take that solution, we do some analysis or sort of cleaning of that data and put it into a format that the PLC understands, and we send it back down to the plant floor. So again, this is not always the case. Not very often have we seen where the plant floor is connecting with some application in the cloud, and in some cases that's not allowed, where this would have to live locally. But what typically happens is that we can make some connection through a firewall and make this happen. So I think this is really kind of the maybe the most important slide here. This is an application where things are happening very quickly. Things are changing very quickly. These trays are moving, like we said, 250 feet per minute, and new packages are arriving all the time. We need to resolve, and we need to get a new solution very, very quickly. And so this is sort of a breakdown on what that looks like. So again, we've got our trays here. They're moving to the left. We don't know about everything on the carousel at every point in time. In fact, there's only a certain distance back that we know about. Sometimes trays may not be able to discharge their package. Sometimes trays show up with packages on them, and we need to consider that in our assignment. So this is where our window opens. Essentially, this is the between these two dotted lines is the width of things that we can optimize. And so once this tray hits this curtain, so to speak, we are developing an assignment for these trays, and these may change depending on what happens from the minute that the window opens to the minute that the window closes, right? Depending on what new packages show up and what new things may arrive. The assignment for a certain tray may change 3 or 4 different times before it's locked in. But looking at the timing diagram, essentially we've got internal and external transit. So this is where we're leaving the local network, the plant network, or going up to the cloud. We're sending the package and tray information. The orange is where we've got our API, this automation intelligence API. We're building our MIP, and then we're giving the solver about 2 seconds. It's not a very long time, right? We've got 2 seconds to give us an optimal solution that maximizes the number of packages on our set of trays. So we need this to happen very quickly. And then essentially it comes back down to us, right? We clean the solution, and then we read it back. So the faster the solve time, right? The more that we can push this line to the left, right? If this curtain, so to speak, were to move to the left, that means we would be getting a solution faster, and we could have more of an opportunity to optimize the trays upstream of that. The width between these two dotted lines would increase, and that would be good. And so that's sort of what the solve time means to us here. And again, it allows us to react to even more recent observations, things that happen, new packages, et cetera. All right. So a few notes on performance. This is obviously something that is dependent on the day and the saturation of packages and even the package mix, but we've seen at most a 7% increase in throughput in a 4-hour time period. Again, just changing the algorithm, just moving away from FIFO, to a mixed integer program. We talked about sensitivity, and these are very sensitive to package mix. You know, the 7% you would only really see up to that point when we've got a lot of big packages, right? Those that need 2 or 3 trays, because those are the ones that we could get a much better density out of by more intelligently assigning them and resequencing away from FIFO. And the other thing too is that to consider, and this isn't on the slide, is that, you know, this depends on having as many packages as your trays can receive, which in the logistics world is typically only around Christmas time, right? October, November, December is when that typically happens, when you're saturating your equipment to 100%. And this is the case where this would really benefit. In reality, we don't give ourselves a 25 or 20 millisecond buffer, as you saw in the last case. We actually use a max solve time of 1,750 milliseconds. And in some of the options that, in our case, the Gurobi solver gives us, we can really make the most use of 1,750 milliseconds. Two things that I'll point out that we use and rely heavily on. One is the ability to stop the optimization at that time. So there's a way that we can say, you have this much time to solve. Give me the best answer you got, whether or not it's optimal. And in most cases it is optimal, but even if it's not, give us an answer. We need something that we need to use. We can't go back to our PLC with our hands up. We need to tell it where these packages need to be assigned. The other thing that's really useful is warm starting. So when we use a warm start, we're basically taking the last solution that we had, which includes probably 3/4 of the same exact trays and packages as we had last time, and we're using that to prime our solver. So it's a way to give it something to start with and not start over from scratch. And typically, at least in our case, leads to a better solutions faster for us. And again, we've talked about this before. There's no mechanical changes here, right? We didn't touch any equipment. We didn't speed up anything. We didn't add trays. We didn't make any mechanical changes. All we did was change the algorithm. We were able to get this much of a boost even in just one day. And that, I think, is really the beauty of the OR tool, and the opportunity for optimization here is that it's very much hands off. It's very cheap, so to speak. It's very quick to implement, and it's obviously a high impact. Now talking about the digital twin, and in this case, we're not able to show specifics of the application due to some privacy constraints, but I want to at least touch on this and describe generally what happens in a digital twin and why we're even talking about it. So, you may remember this diagram from earlier where we're talking about the plant floor. Well, in this case, we can actually recreate the factory floor or the logistics center facility in a digital twin, something that's physics-based, and there's some tools to do that. The idea, though, is that we can control this digital twin with the exact same software that's on the plant floor. Essentially, we take these controllers, these computers, and make them think they're running the real system when really they're controlling just our virtual replica of this system. And so it gives us a really clear picture on how the system will behave in a very complex environment in many cases. The reason why this is important is it allows us to test our algorithm integrated potentially with some other code that controls other systems and mechanics of these systems before it's migrated to the plant floor. So we can throw wrenches at our algorithm. If we have a latency issue, we'll see it. If we get poor quality from our solver, we'll see it. If we don't even beat the algorithm, we will see that. And so it gives our clients the peace of mind that when we go and make these changes and power things on, that we will get the results that we say we're going to give them, again, before they touch anything in the real world. So that's why that's important. All right. Well, that concludes my talk. If you have any questions, again, please feel free to share those in the chat box if one exists during this meeting. And I imagine that I'll be present and able to answer any of your questions. Otherwise, please feel free to email me or call me. You can see my email address and phone number here on the screen. I love hearing ideas. If you think there's a potential application for something similar to this, we'd love to hear it. If you have feedback on this presentation or want to know more about it, I'm also happy to hear your thoughts and feedback there as well. So in any event, thank you for joining me, and have a great day.